Alright, so I want to show that what I have said about exponents does not cause problems for, say, complex numbers, and that when it looks like we're using vectors in the exponents, because you can have positives and negatives and fractions, so all of the reals, which is a vector space, it's a one-dimensional vector space, that is actually trivially, there's some nuance to it, but it is expandable to uh, like the complex plane or you know, whatever. Okay, so first, let's look at what the hell a complex number is, right? So we've got two axes. You have the imaginary and you have the real, right? And those go off forever, and there's your origin, right? Like this. So say we've got two numbers, two components to this, right? You have your real component, and you have your imaginary component, and they come together to give you this guy. This location in the complex plane is your complex number. So, say this is A and this is B. This is A plus BI. Okay? So we can describe it this way, and then there's another component that we could look at to help us describe this, and that's if we draw this line here, and then look at this angle, and let's call this angle phi. So this is the angle above the positive real axis, right? So if you're over here in the second quadrant somewhere, your angle above the positive real axis is going to be over 90 degrees, or over pi on 4 radians. If you're over here in the fourth quadrant, your angle above the real axis is going to be negative, or almost all the way around. Either way you look at it, it works. Okay. So that's the gist of what's going on here. And there's going to be a part where this is going to come into play. Alright, so say we've got... God, there's all kinds of shit on this desk. Say we've got some complex number. I'm just going to call it Z, right? And we're going to raise it to a complex number, but here I want to actually name out the parts. Turns out, naming the parts of this is not going to really help us too much, because in the end results, really the only thing that matters is this magnitude, which has its own length. So, yeah. So this is going to be raised to a real component plus an imaginary component, like that. So this is a complex number raised to a complex number. What are we going to get out of this? Well, we're going to get something that has a magnitude, and so the convention for writing a magnitude is the absolute value symbol with just single line, and your little dude in there inside of it. From physics and engineering, I learned to do a double line like this, just to make it much less ambiguous what's happening, because now it doesn't, there's no possibility that it's an L or a capital I or 1 or something like that. They're definitely these bars that are indicating we're looking at a magnitude. Okay, so it's gonna be a complex number, right? So it's gonna have a distance here. So this distance here is this. That's how long it is. So if A is 1 and B is 1, this is going to be the square root of 2. Yeah, something like that. Okay. So I'm going to have to rename our result. So this is a z, so I'm going to call this sine, just out of my own personal convenience. And then this is going to be multiplied, that's the magnitude. So there's going to be a real component, which is going to be the cosine of the angle that it's lying at, plus the magnitude of sine times the sine of that angle again, times I. So this is the real component, this is the imaginary component. So let's break out what these pieces mean. Okay, the easiest is to kind of like open up what is z, what is z. So this is, let's just use a plus bi, right? So it's that. Now, if that's true, then the magnitude of this, or the complex argument, is another word for it, is square root a squared plus b squared. Hey, look at that, Pythagoras. That's all that is. Okay, this is going to come up in a minute. Now, this angle here, phi, is the angle whose tangent is b on a. No surprises. Rise over run. Opposite over adjacent. That's what the tangent is. So the tangent of this angle will be b over a. So phi will be the angle whose tangent is b over a. That's what that means. Alright, now we're getting there. We just have two more pieces. This, see, where are we at? This angle, rho. And I'm doing it in this order because now rho is going to require this and this. So it makes it shorter to write out if we have those. Okay, rho is going to be the real component times our angle phi. And that's the full real component of the, or yeah, that's the real part, or the part that's coming from the real. This whole thing is real because it's just the measure of an angle, but that's the part that's coming from the real pieces. And then this dude, the I, times the natural logarithm of the magnitude of z. Okay, so there's a lot going on there. This is why I'm just assigning these things to these variables, and you can expand it out if you like, but this is really nice because it makes sense. This means that we're going to have a final vector whose magnitude is line, or it's this. The final vector is line, but the magnitude of line times the base given by that angle, and the magnitude of line times the sine given by that angle, and that's the imaginary component. And then one more piece. So the magnitude of line is going to be the magnitude of z raised to the real component of our thing there, divided by e to the imaginary component times phi, your phase angle, or your complex argument. Okay, so with all of these parts, there you go. That's how it works. Now, there's a shit ton of stuff going on here. There's some backstory that we're not getting into. But if you look at this, nothing in here is beyond basic trigonometry, addition, multiplication, and exponentiation. Nothing in here requires that. So if I've defined all of those things correctly, we're never going to have a problem. We can take this and raise it to the 0 power, and because we've already defined exponents correctly, where 0 to the 0 is 1 by definition, because we paid attention when we were defining how the fuck it works, it's gonna come out correctly. There's nothing here that contradicts what we're doing. Okay? We don't need to be looking at limits, we don't need to be, fucking around with shit. It's just gonna fall out of the definitions of the functions that we've already defined, the operations that we've already defined. There's no magic here. It's just tedium. That's really all that's happening. It's tedium. Right? If you can handle basic trigonometry, if you can handle addition, multiplication, and exponents as I've already defined it, there's no problems here. So there's nothing in this that poses issues. So the way that I have outlined exponentiation, it works just fine for complex bases and complex exponents. No problem whatsoever.